In this example, we'll show how to model a simple allotment in Sirio. So the allotment consists of roads of in total 1,200 square meters, and there are 10 houses that will be connected to the sewer system as well. So each house is of course on private terrain and has on average a roof area of 125 square meters and other paved areas of about 30 square meters. Each house also has a rainwater tank of 5,000 liters and an expected reuse of 100 liters per day. There is also an infiltration basin, so the water of the rainwater tank will overflow into this infiltration basin, and the infiltration basin is modeled according to the GSV rules in Flanders. Once each infiltration basin is full, it will spill onto the public domain, and there we foresee an infiltration conduit of diameter of 600 millimeters, a length of 200 meters, and the invert level is at 12.3 meters above datum. The infiltration conduit is also lying flat or horizontally, so there is no slope. So now I'll show you how to model this simple example in Sirio. So this is the General tab, the opening screen in Sirio, and here first we will add some default model parameters, like the infiltration capacity for instance. Then we don't have to write the infiltration capacity for all the different elements in our system. So in this case the infiltration capacity is 20 millimeters an hour, that's the measured value, and we'll also use safety factors of 2 for the bottom and the side infiltration. So that means that we will actually use an infiltration capacity of 10 millimeters per hour, so 20 divided by 2, in our simulations. That's also according to the Flemish design rules. We leave the simulation parameters as is, you can see in the manual what they precisely mean, and we continue to the tab Model. And here we will provide the different elements that are in our system. So we start off by modeling the houses. Each house is identical, and for this we will use a parcel module. So we only have one parcel module per Sirio model, and this will represent one house. So each house has a rainwater tank, so we will include this one. And the roof area was 125 square meters or 0.0125 hectares. We will use a runoff coefficient of 0.8, again according to the design rules, and a capacity of 5,000 liters. The reuse is 100 liters per day. So then we also have an infiltration basin at each house, and the terrain area was 30 square meters. And using this button, set dimensions according to the GSV law, we can create an infiltration basin that meets the GSV rules of Flanders. You can also see that here. Of course, you can still change the capacity if needed. And here at the bottom you can see the different infiltration parameters. We already supplied them, so they are already filled in. So an infiltration capacity of 20 millimeters per hour. And we will only allow infiltration through the sides. That's a choice that you have to make. And again, we use a safety factor of 2. So with this, we've modeled one house. And then we can continue to our public domain. And for this, I push this button, select the reservoir. And then you can see that you can actually select one of these rectangles in this grid. So it doesn't matter which one you select. I select, for instance, reservoir number 8. And this will be our infiltration conduit. So I also give it a name. And then you can see here that we have a red cross indicating that there are some parameters missing here in this category. Because there are some parameters missing, the reservoir is also shown in red. In this case we have to supply the runoff area as well, and here we only have to use the area of the roads because the houses will be connected differently. So the roads had an area of 1,200 square meters. We can easily calculate the capacity outside the program. This will be 56.5 cubic meters. We can also calculate it using Sirio. I'll show that in a minute. And here we have to specify the number of parcel modules that are connected to this conduit. So this is basically how many houses that are connected to the infiltration conduit. So in this specific case it will be 10. Here we can see the overflow parameters. It's going to surroundings, so that means that the overflow is leaving the model. And here we can also specify some dimensions of the reservoir. So in this case we're going to do that, and if you activate this one you can define the dimensions, and then, and only then, also the water level will be simulated. So we define the dimensions here. It's a simple infiltration conduit, so it's only one conduit, so I select option 2. If your project contains multiple conduits, or if there is it's a connection of multiple conduits and basins, for instance, you should use option 4. I'll show that in a different exercise. But for now we're using option 2, one conduit, and here are the parameters that we have to specify. So it had a diameter of 600 millimeters, a length of 200 meters, and the invert levels up and downstream were 12.3. If you push this button you can also see which curve is being used in the simulation itself. So here you can see different levels and the corresponding storages, so the storage in this conduit. You can also see the overflow crest level. It's at 12.9 meters above datum. So I save and exit. And then you can also see here that the overflow level is now being filled in. You can also see it here on the reservoir itself. And if you want, you could change it as well here. So you can type the desired overflow level and update the capacity accordingly. So the overflow level is being calculated using the capacity here and the dimensions that are defined underneath this button. And then finally we only have to supply the infiltration parameters. So in this case we will use infiltration through the sides. That's regular for a conduit. And we use option 1. That's the simplest option, and then Sirio will automatically calculate during simulations what the wet area is, so the area that can be used for infiltration. And again, these parameters are already filled in. So now we've defined all the parameters in our model. The reservoir itself is also green, and then we can simulate our model using this button here. So now we simulate a 100-year time series, and the results are shown here in this tab, simulation results. On the left hand side you can see the mass balance for the different elements that are in our system. So we have the parcel module, the rainwater tank, the infiltration basin of each house, and this represents one house each time. Then we have also our reservoir, of course, and we have total. Total meaning basically the sum of all the different elements that are in our system, except for the overflow and the through flow. Then we only look at elements that are passing flow to the surroundings. So here in this column you can see that the only incoming flow is of course coming from rainfall. We don't have any other flows. For the outgoing flows we have infiltration, water reuse, and also overflow. And here we can see that we have about 73% of all the rainfall that will fall onto our project, so on the roads but also on the different houses. 73% of that rainfall will go to infiltration, 27% will go into reuse in the houses, and less than 1% will flow, will spill through the overflow. The numbers that you see here are the volumes passing in 100 years. So if you want to know what the average infiltration volume is, for instance, in 1 year, you can simply divide this one by 100. So it's a bit less than 1,000 cubic meters per year that will infiltrate. Here you can also see the maxima that are being simulated and the emptying times for all the different elements. Here at the bottom you can also see this visually for the column total, so then you can immediately see that there was a lot of infiltration, also quite some reuse and very little overflow in the case. On the right hand side you can see some more detailed analysis. Here the overflow volumes and discharges are shown for different empirical return periods. The return periods are shown on a log scale, so that's important. So that means that this is 1 year, 2 years, 3 years, 4 years, and so on. Here we have 10 years, and all the way at the back we have 100 years. So this figure shows us different overflow events that are independent from each other. So each dot, as you can see here, represents one independent overflow event. You can also see the precise dates here at the bottom in this table. So for instance, once every 100 years we will have an overflow event of about 115 cubic meters. Every 20 years, for instance, that's here at this indication, we have an overflow of approximately 30 cubic meters. So this one has a return period of 20 years. So that's how you can read this figure. Here you can also see the total number of overflows in a period of 100 years. In this case it's 32, meaning that on average we will have about once every 3 years an overflow event. And as I already said, you can see here in the table more detailed results as well for all the different events. Here you can see the degree of filling, for instance. This is showing us the percentile. This is the volume, and here you can see the degree of filling. And you can ask this one as well for all the different elements that are in the system. So on the x-axis you can see the percentile, meaning the percentage of time that a certain degree of filling or a lower degree of filling is being reached. So for instance, you can see here 80% of the time, that's a percentile, about 17 or 18% of the infiltration basin is filled or less. That's how you can interpret this figure. So for instance also, you can see here that about 20% of the time our infiltration basin at each house is empty. A final result that I wanted to show in this exercise are the time series. So you can also inspect all the different time series that are being simulated in the model for all elements and all different series that are available. You can also zoom in onto a specific time series using the magnifying glass up to the level, up to a resolution of about 30 seconds. So in the next exercise we will also show you how to add a groundwater level and drainage in the system, and then we will look at two different designs.